first one is R-Visor, and this one is from Arizona State University and University of Novi. Can you start? All right.
Hello everyone, my name is Edwin Kayang and I'll be giving a presentation on R-Visor, an extensible dynamic binary analysis and instrumentation tool for open instruction set architectures. To begin, within the domain of software engineering, binary instrumentation is a very useful technique. So this involves inserting some additional code termed as instrumentation routines into the binary. And we can do this for multiple use cases. For example, we can use it to profile a binary and identify the various bottlenecks. And then once these are identified, we can apply various optimizations and improve the performance of our binary. We can also use it to identify bugs within the binary and patch these bugs. And that falls within the realm of software debugging and testing. So there are two ways to go about binary instrumentation. The first one is the static method, and this produces a new binary containing all the instrumentation routines. Alternatively, we can do dynamic binary instrumentation where we execute the binary and make the changes at runtime. So as such, no new binary is produced. And this dynamic method also allows for more fine-grained control over the instrumentation process. Binary instrumentation is a mature field with over 20 years of development, and within the landscape of binary instrumentation, there have been multiple tools developed, for example, Intel Pin, DynamoRIO, and Valgrind. However, a common trend is that initial versions of these tools are built to support specific architectures such as x86 or ARch. And based on the instruction set architecture that these architectures use, they are classed as closed ISAs. That is, they are bound by restrictive licenses, preventing third parties from being able to develop new extensions or instructions on top of these architectures. And what this means is that if any tool is being developed for such an ISA, there wouldn't be a hard requirement for extensibility. And so if a new extension were to come up in such an ISA, what that will mean is that a user would have to go into the code base of the binary instrumentation to search for all the locations that need to be changed in order to account for this new extension and then make those changes manually. Now, to do this, the user would need to have a deep understanding of how the tool works. And if the changes are not made correctly, you could end up introducing bugs into the tool which would taint the correctness of the instrumentation process. This problem becomes more serious when we consider the rise of open ISAs in our modern times. With open ISAs, their main selling point is their non-restrictive license, which means that third parties are freely able to develop instructions or extensions which can help accelerate workloads in various domains. And in reality, new extensions are actively being developed for these ISAs. So for example, if we take RISC-V, one of the popular open ISAs, you'd find out that in 2024, they ratified 15 new extensions. And if we look through the publication history, you'd see that a lot more extensions were developed for them, although these extensions have been unratified. And when we consider all this, it brings about a new requirement for binary instrumentation tools for such architectures. And that is, the binary instrumentation tool needs to be extensible to account for the new extensions that are developed for such ISAs. And that brings us to our problem statement. So these existing binary instrumentation tools were not developed with the extensibility feature as their core requirement. And what that means is that if the underlying ISA releases a new feature, then developers would have to go into the tool's code base and manually make changes to support the new ISA feature. And so this can be a very laborious and intensive process, and it can also introduce bugs that would end up tainting the correctness of the instrumentation process. So to solve this, what we need is an extensible binary instrumentation tool. And if done correctly, it will enable the tool to more easily be able to keep pace with these evolving open ISAs. To solve this problem, we present R-Visor. And R-Visor is an extensible dynamic binary instrumentation tool which we have built to solve the extensibility needs for open architectures. And we focus on certain features such as the low overhead so that it would be useful in most instrumentation use cases, and we also give it a just-in-time based execution model for instrumenting the binaries. Additionally, we include a flexible instrumentation API which would allow users to write custom routines. So to solve the extensibility aspect, we make use of the ArchVisor domain-specific language. And so R-Visor uses the ArchVisor DSL to specify the various new ISA features, and once these have been specified, they will be automatically integrated back into R-Visor for users to instrument while accounting for these new ISA features. Now let's take a look at the architecture of R-Visor. So first off, we start with a target binary, which is an ELF binary, and we send that to the ELF parser, which extracts the relevant segments from the binary. Next, the code gets sent to the decoder, which translates it into an interpretable form for the rest of the tool. Then we segment our binary into traces using our basic block allocator. So for the purpose of R-Visor, traces first start off as basic blocks, and these are stored in the code cache while keeping track of the locations of the various traces. Next, we have a dispatcher which manages the control flow within the code cache. So once a trace completes execution, control switches to the dispatcher, and the dispatcher must select the next trace to be executed on the hardware. Finally, we include an instrumentation API which allows users to write their routines as custom C functions. And it also allows them to specify when the routine should be called during execution. So traces are one of the areas where we had to make a lot of design decisions for R-Visor. And so within the context of R-Visor, we begin each trace as a basic block. And since after the trace executes, we need to return control to the dispatcher, what we do is that we include a stub at the end of each trace. So the stub contains code to trigger a context switch routine, and that enables us to return control to the dispatcher. Now, another consideration we need to make with respect to our traces is that we need to ensure that they run with minimal overhead. So that's in terms of both execution and memory. And so we use certain optimizations to achieve this. The first of these optimizations is termed trace linking. And what this allows us to do is that we're able to connect two traces to each other within the code cache without the intervention of the dispatcher. So it helps reduce the number of context switches between R-Visor and the code cache, which would reduce the execution overhead. We also include a second optimization known as stub regions. So since the stub code is similar for most traces, what we are able to do is that we store the stub code within a centralized location inside the code cache, and we terminate each trace with a jump instruction to that stub region. So this effectively reduces the amount of stub code that we place within the code cache and reduces the total memory overhead of R-Visor. So now that we have the architecture set for R-Visor, the next thing we need to consider is the extensibility aspect. So to do that, we need to look at the various components and their different requirements for extensibility. For example, the decoder and encoder need an understanding of how each instruction should be broken down into its subcomponents. The basic block allocator would need to understand the various control flow instructions within the ISA, and the instrumentation API would need an understanding of the registers and instructions so that it can relay this information to the user for use within the instrumentation routines. Now, in any traditional tool, if there's any ISA change, this has to be specified within the source of the underlying binary instrumentation tool. However, we can help automate this by using a DSL, where we can concisely specify the various ISA components, and these can be integrated back into the tool. And we're able to achieve this using ArchVisor. Now, ArchVisor is a source-to-source domain-specific language which we use to integrate these new ISA features back into R-Visor. So first off, we start by writing the ArchVisor sources, and we pass these to a code synthesizer which is able to generate extensions within the source language of our R-Visor tool, and these two are compiled together to produce an R-Visor binary which can be executed together with a target binary to produce our instrumentation output. To design ArchVisor, the first thing we need to consider is the grammar. And in our case, we're going to look at the various components of the ISA that we need to specify. So for our initial version, we look at the instructions, the registers, and we also consider the instruction types, since these control how an instruction should be encoded or decoded. After considering these, we're able to develop ArchVisor to have three different data types. The first is the instruction type or int type, which specifies the various components of each instruction and their locations within the binary instruction. And then next we use the instruction type to give specific values to the various components of the instruction. And finally, we have the reg file type, which specifies the various registers within a register file together with their load or store instructions. And this helps us with the context switching process. We implemented R-Visor in roughly 8,000 lines of C code while using custom versions of certain libraries and data structures. For example, with the elf parser, rather than using a library like libelf, we used the deploting process to strip down the amount of code that went into the final version of R-Visor. And R-Visor currently supports RISC-V, specifically the RV64 GC toolchain, as this is a general toolchain for most workloads. Finally, we have an ArchVisor backend created specifically for R-Visor, and this supports features such as the custom instruction groups, which can be used as target points during the instrumentation process. To evaluate R-Visor, this is the experimental setup we consider. First off, the hardware consists of a trireme RISC-V processor hosted on an FPGA, and then for our operating system, we use a minimal BusyBox hosting a Linux kernel. Then to evaluate the performance of R-Visor, we consider the EMBench benchmark suite, which is made up of about 23 binaries for deeply embedded systems. Then to compare our performance of R-Visor against state-of-the-art tools, we compare R-Visor against DynamoRIO, which is an industry standard dynamic binary instrumentation tool that had a port developed for RISC-V in 2024. Finally, the instrumentation routines that we evaluate on are the no instrumentation routine, where we just consider the execution overhead of running the binary with the instrumentation tool. And we also look at the basic block counting routine, and this routine dynamically executes the binary and counts the number of basic blocks that were executed. So first off, we look at the comparison of the execution overheads of both R-Visor and DynamoRIO, and using both the no instrumentation and basic block counting routines. And in both cases, we see that R-Visor is able to maintain a lower overhead. And if we look at the basic block counting example, we can see that R-Visor is able to have a more minimal increase in overhead as compared to DynamoRIO. And this trend continues when we look at the memory overhead comparison. Moreover, R-Visor is able to maintain consistently less overhead across all the binaries that we tested on. Then to compare the overhead of ArchVisor, we look at the number of lines of code required to support certain extensions in both R-Visor and DynamoRIO. So in this case, we use the floating point and compressed extensions, as these are available already in DynamoRIO. And in both cases, we can see that there's a substantial reduction in code needed in R-Visor to support these extensions. And this goes to show the usefulness of ArchVisor in achieving the extensibility within our binary instrumentation tool. Next, we move on to our use case, which is instruction emulation. And this can become useful when we have hardware support for certain ISA features, but we don't have that same support in the compiler. So in this case, the hardware supports compressed instructions, but the compiler cannot support compressed instructions. So we need an instrumentation routine that will be able to translate the uncompressed instructions to their compressed versions. To provide this support, we need to first create our ArchVisor sources, and these are going to consist of the instructions that have the compressed equivalent. And as you can see, we're assigning these the DBT group to help us with the instrumentation routine. And then once we've declared all of these instructions, we declare their compressed equivalent so that we can translate from the uncompressed to the compressed format. Next, within our instrumentation routine, we start by using the routine to match the various uncompressed instructions and replace them with their compressed equivalent. Then within our main function, we invoke the instrumentation routine whenever we encounter the DBT group, and this helps provide lower overhead than us running the instrumentation routine on every instruction that we encounter. So on executing these benchmarks on the EMBench suite, we're able to get an average size reduction of about 16.94% after we translate the uncompressed instructions to their compressed format. In the future, we want to look more towards making R-Visor a more comprehensive tool, and what this would look like is adding support for more advanced program features such as multi-threading, self-modifying code, and dynamically linked libraries, as these are features supported by a lot of general purpose binaries. And we'd also want to look at handling OS level functionality, privileged functions such as context switches and interrupts, to make it be able to instrument more comprehensively. Then within the realm of ArchVisor, we want to look at extending it to do things like allowing the creation of instrumentation routines directly within the ArchVisor sources rather than using a separate language. And we also want to look at integrating ArchVisor into other areas of system development, for example, hardware simulations. In conclusion, within this presentation, we have looked at R-Visor, which is an extensible, just-in-time based binary instrumentation engine that we have built specifically for open ISAs, and it makes use of the ArchVisor domain-specific language, and that helps it to achieve the extensibility and solve the problem of extending traditional binary instrumentation tools. And this DSL allows it to provide a concise way of integrating the new ISA features back into the R-Visor tool. Within our evaluation, we are able to show that R-Visor has low runtime overhead, memory footprint, and code overhead. Finally, the R-Visor tool is open source and made publicly available under an open source license. I would like to thank the organizers of LCTES for giving us the opportunity to present our paper during this conference, and I'll be available to answer any questions concerning the work. Thank you.
Yes, then let's take questions from the audience. No questions, no comments? Please.
First off, thanks for the talk. I noticed that there is a strong parallel between the architecture of a tool like QEMU and R-Visor. Have you looked at all the crazy optimizations they do to make everything as fast as possible?
So we haven't looked at the optimizations related to QEMU specifically, but we've compared the optimizations to other dynamic binary instrumentation tools, so more mature tools. And so we do borrow some inspiration from the optimizations they implemented. For example, we implemented similar versions of their methodology for the trace linking.
All right, thanks.
Any questions? Okay, then let's thank the authors and presenters. Thank you.